All right, good morning, Chem 30. Today we're going to look at ice tables and where we use them and why we use them. And so, really, like the last video, we talked about finding our equilibrium constant, our Kc value. Okay, one thing to remember is that Kc value, it's a ratio, it doesn't have units. Okay, it's just kind of telling us whether it favors the forward reaction or reverse reaction, or it's kind of even. Okay, but to find those to find our Kc value, we need to set up our equilibrium constant equation, and then with that, all of our values that we use have to be at um, equilibrium. So what happens if we don't know our values at equilibrium? So if it gives us our initial values and says like what's the change, things like that. So that's where we're going to create and use what's called an ice table. Okay, so it's just a way to organize, okay, our information that we have so that we can then solve for our numbers at equilibrium and then put those numbers into our equilibrium constant equation. So the reason it's called an ice table is just the I represents initial molar concentration of the reactants and products. C is the amount of change in each of the reactants and products. Okay, and then E represents the molar concentrations of reactants and products at equilibrium. And that's what we need then. Once we have those numbers, we can then solve for our Kc value. Okay, so to set it up, you follow these steps. You want to write out the equilibrium equation, okay, and then make a column below each reactant and product. So like this. So you'd start out, you'd write your balance chemical equation. That's what it means by write out the equilibrium equation. Okay, and then like you just have the double-sided arrow to show it's at equilibrium. Okay, you label the rows with initial, change, and equilibrium. So ICE, you don't have to actually write out initial, change, and equilibrium. You just write out ICE, and that's why we call them ice tables. Okay, fill in the table with all the known values that are available. In most cases, like you'll start with a known value, like this will be 0.100 and then like moles per liter. Okay, usually these are going to start at 0, right? Because when you first start with the reactant, there is no product. Okay, so that's where you kind of start. These are just made up numbers. I'm not using an example or anything. We'll do that more on the next page. Okay, so we got that. We filled in all the known values. Sometimes it'll give you a value down here, and you can use that to kind of work backwards. Okay, there's a couple different types, and we'll talk about those as we go through on where you have to solve and where you have to find. Okay, you're going to use X to represent the value that you do not know. Again, so like really in change, you're going to use an X to represent the change. So the change in our initial concentration, some of this concentration is going to go down to produce these two things. So this is going to be minus X, but because there's a 2 here, it's going to be minus 2X. Over here, they're both going to go up by the value of X. Okay, and then from there, the equilibrium is going to be your initial and then added to the change. So like this would be 0.100 minus 2x. So that's when we're filling in another box with the expression. So we're going to fill in the expression, not the actual answer. Okay, that's included in our knowns and unknowns. So then this is x, this would be x because it's 0 plus x. Okay, and then from like your known value, you should be given more information in the question. So then you could, like if it said your concentration at equilibrium is 0.05 or something, then you can solve for x and then know what these values are too, because they're x. So we'll do an example here on the next page. Okay, and kind of show you the steps as you're going through, okay, and how to solve for it. So the sample problem, so we're experimentally determining the equilibrium constant for the decomposition of hydrogen iodide at 453 degrees Celsius. So it's one thing to note, like they tell us the temperature, but the temperature doesn't change. It's just saying that like this reaction is taking place at that temperature. Okay, and then you fill evacuated 2-liter flask, so that's our volume. And then with our, we have 0.2 moles of hydrogen iodide, so that's our, so we'll have to go moles divided by volume to get our concentration. Okay, we let the gas decompose into hydrogen gas and iodine gas until you reach equilibrium. Okay, you're able to determine that the concentration of hydrogen iodide was 0.078 moles per liter at equilibrium. Okay, and so then from this, you need to determine the concentration of hydrogen and iodine gas. So really, again, like we follow those steps. So we set up our ice table. So we write down our balanced equation. Okay, IC on the side. Sometimes I like to kind of split these up just so they're a little more clear. Okay, it's up to you. We write in then, so our initial concentrations. So again, initially we have 0.2 moles of hydrogen iodide in a 2-liter flask. So we have 0.1 moles. So that's what we're starting. Okay, there is no hydrogen or iodine to start with in that flask. So they're both at 0. Okay, again, from stoichiometry of the reaction, the mole ratio of the hydrogen gas to iodine is 1:1. Therefore, at equilibrium, the concentration of hydrogen gas and iodine gas are going to be the same. So we're going to let X represent those numbers at equilibrium. So we're going to place this X in these boxes. Again, it's going to be plus X because like their concentrations are going to go up. Okay, and so yeah, we put those symbols on the table. Okay, then we see that like we have a 2 in front of the hydrogen iodide. So that's where we get the minus 2X. That goes in here for the change. And then we write in our expressions like this. Okay, so we did that kind of on the last page. Okay, now we need to calculate to solve for X. So earlier up here, we're given this. This is at equilibrium. So our 0.1 minus 2x, this here is going to be equal to our number at equilibrium. So 0.1 moles per liter minus 2x is equal to 0.078 moles per liter. So now just rearranging this, we want to solve for x. So we'd subtract the 0.01 from both sides, okay, and then divide by -2, and we get our value of x is 0.011. Okay, so that's, now we know that this number and this number is both 0.011. Okay, and then from there, now we're putting in for our we want to solve for equilibrium constant, so we just put it into our equilibrium constant formula. Okay, we put our numbers in that we know. Okay, and we get our Kc is approximately 0.020, and again, no units there. Okay, and so that one, it's going to favor our reactants. Okay, so that example is kind of the most basic form of how we could solve for, using the ice table to solve for equilibrium constant. Okay, generally, it's best to let X represent the substance with the smallest coefficient in the chemical equation, because then it avoids fractional values of X in the equilibrium expression. Okay, so solving for problems with very small equilibrium constants. Okay, so in many cases, the mathematical equation that you create when you substitute expressions in the formulas for equilibrium constant you end up with a quadratic equation. So like the expression 0.2 minus x times 0.3 minus x equals -2x squared. Okay, when you're setting up, you end up with the expression 2x squared plus 0.5x minus 0.06 equals 0. So you could always use your quadratic formula, okay, which you learned in Math 30, or actually Math 20, you go over this, okay, to solve for x. Okay, but in chemistry, okay, in these situations, we're going to make an approximation to basically simplify the equation. So if the equilibrium constant for a reaction is very small, then very small amount of product is going to be present. right? Because it's going to favor the reactants. Okay, and the amount of reactants at equilibrium will be almost the same as the initial amount. So assume that the initial amount of the reaction is 0.65, and the change in that amount of the reactant is 0.000032. If you were to like subtract that, so our initial minus final, they really, when we use the rule for significant digits and we're rounding to 2 sig digs, okay, we're going to end up with the same number, 0.065. So yeah, so again, for the rule for adding and subtracting, okay, it's the precision rule, which is whichever one, it can't have more decimal places than the data with the fewest number. So when we round this number to 3 decimal places, we get the exact same number we started with. So therefore, when the equilibrium constant is very small, we can make an approximation that the amount of reactants at equilibrium is the same as the initial concentration. So to decide whether to use this or not, okay, we use what's called the rule of 1000. So an approximation can be made if the initial concentration of the reactants are at least 1000 times greater than the Kc. So basically, you just take your initial reactant concentration and divide it by the Kc value. If that number is greater than 1000, okay, then we don't have to, like the minus x from up here, we can take that out. That no longer matters because it's such a small number that we don't need it. So then when we put this in our equation, we just have 0.2 times 0.3 equals x squared. It's a lot easier to solve for x because we don't have this polynomial or binomials that we have to multiply together. Okay, so basically, yeah, if we use the rule of 1000 and in like pretty much every case, the rule of 1000 is going to work and give you a number greater than 1000, so you don't have to do the minus x. Okay, so that's, yeah, the change in concentration of the reactants is insignificant and can be approximated to 0 or ignored. So basically, we just get rid of those minus x's in those cases. Okay, I will do some examples of these. Okay, so it's a lot easier to kind of see when we do those examples. Okay, note, no practice section or review question in this text will require you actually to use a quadratic formula to solve an acid ionization constant problem. However, you may be asked to state whether the given problem would require use of the formula for a solution. So basically, if the rule of 1000 fails, as far as you would have to go, you don't have to actually use the quadratic formula. In your answer, you just state, I would use the quadratic formula to solve for this answer, and then you're done. Okay, and so that's one thing you don't have to worry about, is actually using the quadratic formula. It's more just if, yeah, this, after you check this, if it doesn't give you a number greater than 1000, you'd say I'd use a quadratic formula. I'm going to do a new video to do all these examples, so you'll refer to the next video to see how to solve for these using the ICE table. Again, showing the different ways, like the backwards ICE table, things like that. So if you're given equilibrium constant, how to kind of work backwards. So those will be on the next video. Okay, and we'll go with that.